Hello, everyone. It's 10 past the hour and we're about to start. I am very excited to present the next speaker, who is from New Hampshire, although right now she's joining us from New Zealand, Dr. Julie Jakubowski. She is an oceanographer at Med Ocean Solutions, a division of the Meteorological Service of New Zealand, based in Raglan, New Zealand. Where her focus is on obtaining ocean observations for public use and assimilation into ocean models as part of the Moana project. Julie holds a PhD from the Massachusetts Institute of Technology and Woods Hole Oceanographic Institution Joint Program in Physical Oceanography, where she studied ocean circulation around the Galapagos archipelago using autonomous underwater vehicles, the spray gliders. Previously, Julie obtained a bachelor's degree in mechanical engineering and in physics at Bucknell University, and then worked for several years at NASA's Jet Propulsion Laboratory as an instrument mechanical engineer. As the team lead of the Tiro Moana workstream for the Moana project, Julie is directing the deployment of Mangopare temperature and pressure sensors with the goal of obtaining subsurface measurements from New Zealand's oceans to better inform the public on changing ocean temperatures. You're all welcome to ask questions, write them in the chat or in the chat window during the presentation, and either Nicole or I will share it during the talk, or you can wait until the end of it. And also, please keep yourself muted during the talk. So Julie, it's your turn.
All right, I will do my best to share my screen again. So share. And we'll go. All right, thank you very much. So as Coral mentioned, I'm Julie Jakubowski, and I will be talking about the Moana project's Tiro Moana. So welcome to Saturday morning here in New Zealand, and thank you everyone for joining us on, I think, most people's Friday afternoon, except for those brave souls who woke up this morning to do this here on the other time zone. So I am an oceanographic data scientist and physical oceanographer at MedOcean in Raglan. And the primary project that I've been working on is called the Moana project. So I'm going to give a little bit of an overview on the Moana project before I get into the Te Tira Moana, or Eyes on the Sea aspect of the project. So the Moana project is a New Zealand federally funded 5-year project with the goal of vastly improving our understanding of ocean circulation, connectivity, and marine heat waves to support an enduring seafood sector around New Zealand. And we do that by providing improved ocean data, hindcast, forecast, and data products to the New Zealand ocean stakeholders. So there are 4 main components to the Moana project. It's divided into 4 themes. And I'm the team lead for the Te Tira Moana theme. And the focus of this talk will be essentially ocean observations around New Zealand and how the Moana project is looking to improve the availability of those observations. So it includes 2 main themes within that, being applying the Internet of Things concept to improve the ocean observations that we have. So that's obtaining new ocean observations around the New Zealand EEZ, or Exclusive Economic Zone. And then also cataloging and making available existing ocean observations from around New Zealand. Okay. So before I get into that, again, I'm going to do a little bit of an overview of the Moana project, or at least my best shot at it. So the Moana project has about 65 researchers and technicians and a whole range of groups of people working in it. So obviously I can't cover it all here. But as I said, I'm the team lead of the Te Tira Moana observation aspect. But once we have these observations, and I'll talk about how we get them, we provide them to the other themes of the Moana project. So there's the Naripo o Te Moana team, which focuses on hydrodynamic ocean modeling. For people who are less familiar with hydrodynamic ocean modeling, this basically means we use physical equations to try to calculate the state of the ocean around the world based on things like what the atmosphere is doing. And so that means we get, for each location in the ocean, we can calculate the temperature, the pressure, the density, the salinity, things like that. And that helps us understand how the ocean moves. For people who are more familiar with ocean modeling, within the Moana project, there's a backbone ocean model, which covers the region around New Zealand, and that's a ROMS ocean model. And we will be assimilating the ocean observations from Tiro Moana via 4D VAR into that backbone model. And we also have some nested regional models also that are part of that theme of the Moana project. We also have Te Hona Moana, which is the connectivity team. And they use observations of biology around New Zealand. And they are looking to understand why certain species of, for example, green mussels are found where they're found and where they come from. And so they also use the physical oceanographic observations and the ocean model results to do their work, and then provide back their results to us. So it's a two-way interaction. And we also have the Hey Papa Moana team. So the Hey Papa Moana team is basically focused on creating a cross-cultural ocean knowledge platform to inform iwi interests. So iwi is a Maori word, which basically means an extended group, or it's often translated as a tribe. And in New Zealand, they have political power and government power. And so we have iwi partners. There's a tribe in the Bay of Plenty called Whakatohea, an iwi, that we work very closely with, that's heavily involved in the Moana project. And they both provide to the project, they research Mataranga Maori, which is Maori traditional knowledge of the ocean. So as they've lived here for hundreds of years, they have a lot of traditional knowledge of where the ocean currents move, where kai, moana, or seafood comes from. And we use that to inform our modeling and our observations. And then they also ensure that the results that we get from this project are used to benefit iwi. And so there's 3 other boxes on this slide, which basically focus on making sure that the output of this project has benefits New Zealand wide. And there's a wide range of people working on that. And it's something we consider in all of the other teams and everything we're working on, to make sure that as we have model results, we have observations, they get to the people they need to go to in a way that is useful to them. So now I'm going to focus on Te Tiro Moana. And the big picture is basically improving the availability of ocean observations from around all of New Zealand. As I said, we have 2 components of that, basically finding the observations that already exist, quality controlling them and making them available, and then obtaining new ocean observations. I put a figure here that classifies the observations we're looking at. Now this figure is very approximate, but it's just to get an idea of why we have 2 different categories of observations here. So the first one is near real-time observations. And those are any that are obtained within the last 24 to 72-ish hours. Again, that's also an approximate number. But the idea is that we get the ocean observations back to us at MetOcean or in the Moana project very soon after they're actually made. And the reason for that is because those observations can be assimilated into ocean models. And what that means is ocean models use equations to calculate the state of the ocean at any given point in space and time. But if we have actual observations, we can force the ocean models at those locations where the observations occur to match the observations, and it makes our ocean models a lot better. And once we do that, we can improve both our ocean model forecasts and our hindcasts. So that's things like calculating the temperature at any given location in the ocean. And that's really important now because we see phenomena called marine heat waves, where we get really high ocean temperatures over a period of a few days or longer. And that impacts a lot of things in the ocean, like seafood, the fish, the ecology. And so we need to understand how marine heat waves work. If we can improve our ocean models, we understand that better. So the second category of observations are historical observations. So that for us is anything that's older than about 72 hours, but that could go back to 100 years. And we use those to both create a product, an ocean temperature product, so that we can look back and say, this is what the temperature actually was 15 years ago. And also to verify our models. So we're calculating the ocean state in our ocean models, but then we need to understand how good they actually are. And to do that, we compare to ocean observations in the past. And so we create from that, again, both better forecasts of the ocean state and better hindcasts. And also we can create subsurface temperature products. And the reason this is important is because we have satellites that go around the whole globe, and we get really good observations of the surface of the ocean. Really good being depending on what you're doing exactly. If you're doing really small scale things, it might not be as good, but we have around the ocean many fewer observations below the surface. And so through trying to find stranded oceanographic data or data that already exists and making it available and getting new subsurface ocean observations, we're trying to improve that. So before I get into that, I would like to cover the data sharing principles that we're using in this project. So the first one is FAIR, which I think many people in oceanography in particular have heard of. So this means the observations and the model data, any oceanographic data, should be findable, accessible, interoperable, and reusable. And basically, the big picture here is making sure that any data we have about the ocean is actually useful to people. So if it's hidden on a hard drive somewhere that no one, even potentially the owner of the hard drive, knows about, then it's not useful. But if we can find those observations, catalog them, and make them available to people with information about what exactly they are, then scientists or other users can actually use it. The other principle is CARE, which stands for collective benefit, authority to control, responsibility, and ethics. And this focuses on indigenous benefit from the project. And the idea is that indigenous groups, for example, the Maori, have a certain value system that goes along with indigenous knowledge. And sometimes when we share data, that value system doesn't necessarily get communicated with the data. So this can be things like only some iwi have access to certain information, or information should be treated a certain way. To do that, we're working with Maui Hudson, who's the theme lead for one of the teams in the Moana project, who is also working with international collaborators on how to label data exactly and what the best process is for making sure that indigenous values get carried along with observations or with model data or with biological data as the project progresses. And one of the ways of doing that is applying traditional knowledge labels to our data, and we're working on incorporating that into our databases as the project continues. We also make sure that we save our data in internationally compliant formats. So for much of our oceanographic data, it's in CF compliant format. And one of the benefits of that is it includes the metadata for the observations, so that when someone opens the file, they know exactly what they're looking at and they know how they can use it. And then wherever possible, we are working to make our observations and our model results open access so that the broader New Zealand community can benefit from it. So the first of our two observation categories is historical observations. And so, as I said, we're looking at cataloging the observations that already exist around New Zealand. So on the right here is a figure of CTD profiles from trawl surveys provided by NIWA and MPI around New Zealand from 2002 to 2017. So this is the type of data set we're looking at trying to catalog and then provide access to. This particular data set is already made publicly available, and I'll explain how that is in a little bit. So this includes all kinds of physical ocean observations. So CTDs and XBTs, for those who aren't familiar, they measure temperature and salinity below the surface of the ocean at basically one location, one spatial point in time. gliders, moorings, ships of opportunity, long-term temperature records. So anybody who holds ocean observations around New Zealand, we reach out to them, try to get access to them if they need to be quality controlled. We work with them on that. We also are incorporating into our models near real-time global programs that already exist, like Argo and Drifters, and near real-time local programs such as tide gauges and wave buoys. We take all that data and then ingest it into a MetOcean observation database where the modeling team can work with it. So we're in the process of doing that. And as we go through this process, we also encourage any data holders to make their data publicly available via the New Zealand Ocean Data Network, or the NZODN, and I'll cover that in the next slide, whenever possible. So we recognize that there are times where that is not possible due to legal agreements, but when it is possible, we strongly encourage open access, ideally free open access to oceanographic observations. And so, as I said, all those observations for the purpose of the Moana project are then added to a database that we hold here that the modeling team can access through one interface called the Ops API. So the NZODN is a web portal that stores ocean observations from New Zealand. So this is in conjunction with NIWA, which is the National Institute of Water and Atmospheric Research here in New Zealand, LINZ, which is Land Information New Zealand, and IMOS Australia. So the NZODN is based on Australia's AODN. So we've worked closely with them to create a similar portal in New Zealand. And this hardware and software management is done by NIWA. We're working through, as part of the Moana project, exactly how to store all of this data. So NIWA can store some, other organizations can store it and then push their data to the portal. So that's something that's in progress now. But right now, you can go on the NZODN website, and there are oceanographic data sets available there that you can select by region, by time, and download the actual data. And that number of available data sets is growing as we encourage data holders to share their data, and often they're very willing to do that, and we're just looking for a way to do it. So we're also working in collaboration with LINZ, as I mentioned, to develop a nationwide marine data catalog. So LINZ is going to all of the organizations they can think of that might have oceanographic data and creating a catalog in one place. That catalog, however, doesn't actually hold all of the observations, so it will point back to the NZODN where the actual data is held and where you can access it and download it. And data on there is open to anyone, so anyone here could go on that website and download CTD profiles from trawl surveys around New Zealand. So the current capability of the NZODN includes cataloging historical data only, but we're hoping in the future to add near real-time data in addition to that. Another aspect of the Tiro Moana theme is quality control of physical ocean observations. So it's one thing to actually have measurements, but they need to be quality controlled before most of the time they're useful to scientists or to other users. So we're working on building a quality control program here. So that includes both historical and near real-time data sets. To upload data to the NZODN, we suggest that they have data quality controlled to documented international standards. It's not a requirement, but it's much more useful for people if that does happen. And so some organizations don't have the capability to do that due to resources or expertise. And so we've been assisting some organizations with developing a QC plan. In some cases, we actually quality control the data ourselves. We have two types of quality control. There's manual quality control, which is applied to certain types of instruments, certain types of observations. And we've worked closely with Beck Cali at IMOS to be trained in using the MQuest software that they use And then near real-time observations are automatically quality controlled via a software package that we've developed here at MetOcean. So in some cases, we actually do that quality control and then provide the quality control data back to the data holders. And we're also developing a new near real-time quality control set of procedures that applies to fishing data. And I'll cover that a bit later. And that's in collaboration with the Bering Data Collective in Denmark. All right, so that's the historical data part of Tiro Moana. The next section is obtaining new near real-time ocean observations. So I mentioned briefly that we are using the global Argo observations in our ocean models to improve our ocean models. So Argo is a global program that deploys instruments called Argo floats around the planet. I think there's about 3,000 Argo profiles in the ocean right now. That number might be wrong, but it's somewhere in the thousands. And an Argo float starts at the surface and it profiles between the surface and 2,000 meters depth. And when it does that, it measures temperature and salinity. And then it parks itself at 1,000 meters depth. And the ocean currents carry Argo floats all over the ocean. When they return to the surface, they send their observations back to Argo processing centers around the world. And so it's an amazing global program that gives us subsurface observations of the ocean all over the earth. One of the features of Argo, though, is that they're parked at 1,000 meters depth when the currents carry them. And so you can look here at this figure where I show the average number of Argo profiles per day between 2007 and 2017 around New Zealand. And you can see that most of them are sort of around this 0.01 Argo events per day in each little box. And that's actually not too bad considering it's a global program and we get a lot of value out of those Argo floats. But if you look at this 1,000 meter line here, so this is where the depth of the ocean is 1,000 meters. You notice that inside of that, it's pretty white, which means there are no Argo events per day. And that's because of this parking depth of 1,000 meters where the Argo floats are being carried by the currents. If they're at 1,000 meters and they're carried by the currents, they can't really make it into shallower water as easily. It happens sometimes, but not as often. And so the question is, how can we use untapped resources to fill this observation gap around New Zealand? New Zealand has a really big exclusive economic zone, or EEZ, and it has a lot of commercial fishing activity. So we have about 650 commercial fishing vessels that are active right now this year in New Zealand. And when you look at where those fishing events happen and overlay them on the Argo profiles, you can see that the average fishing events per day in orange can reach up to about 5, and they're pretty much exactly in this region where the Argo profiles or the Argo floats can't go. So we looked at this with the Bering Data Collective in a paper by Van Branken et al. 2020 in different regions around the world, and we see the same kind of pattern where the coastal regions have a lot less subsurface ocean observations. So how can we fill this gap? Oh, and if you look at this plot on the right here, this is from 2007 to 2017 on the x-axis, and the y-axis is the average Argo profiles per day. It's between about 3 and 6 from the New Zealand region, so basically it's in this map region. And on the right-hand side, we have average fishing events per day, and it's closer to about 300, and they're all in this coastal region or shallower region. So how can we fill this gap, potentially using fishing events? Well, the Moana project has developed a new temperature and depth sensor called Mango Pare. So it's developed with our technology partner Zebratech, which is a New Zealand company led by John Radford. Mango Pare was named by Danny Paruru from the Whakatohea iwi, and it means hammerhead shark. And that name comes from the fact that hammerhead sharks have really good senses and are really good at observing the ocean. So the idea of the sensor, which is shown here in the bottom left, it's about this big. I wish I had one to show everyone, but I just sent the two we had back for calibration. So the idea is the sensor is mounted on fishing gear, commercial fishing gear. When the fishing gear is deployed, it measures the ocean temperature and pressure. When the sensor returns to the vessel, it transfers its observations via satellite or 4G back to the cloud, where we quality control the data, integrate it with our ocean models, update our ocean forecasts and hindcasts, and then we deliver that information back to the fishers via smart tools. So it's this full circle of the fishing sector taking the observations, informing science, and then us returning those results to them so they can improve their fishing. We're currently in the advanced trial stage of the sensor. So we've been deploying it on vessels. I think the earliest one was about July, but a more rolled out version of the trials started in October due to a bit of a COVID delay. So these trials are happening in collaboration with the New Zealand seafood and fishing sector. And that includes the Deepwater Group, Fisheries Inshore New Zealand Rock Lobster. And what we found is that the fishing organizations around New Zealand are really interested in improving their knowledge of ocean temperature below the surface. And there's a lot of reasons for that. But one of them is that it makes their fishing more efficient if they can target the species they're actually supposed to be catching and avoid the species that they're not supposed to be catching. So bycatch is a big problem in the fishing industry, and it's a problem from a sustainability and a conservation perspective also. And so by understanding where the fish might be based on temperature, they can avoid the fish that they're not supposed to be catching. And that helps create a more sustainable fishing sector. So we've had really good input from them. They've been very motivated to participate in this. And we get emails on a regular basis from fishing companies that want to participate and are looking to put sensors on their vessels. We also have our international collaborators, being the Bering Data Collective in Denmark, and they are deploying sensors. I think they have about 8 sensors right now around the world, so they can test them in places like Greenland in environments that we don't have here in New Zealand, and we've gotten some really good results from that. So the data pathway looks like this. We put the sensor on the vessel. It automatically starts measuring when it hits the water. As the fishing gear is deployed to whatever depth they're fishing at, it measures on the way down throughout the deployment of the fishing gear. And then when the sensor and the fishing gear return to the vessel, the sensor automatically offloads its data via Bluetooth to a deck unit that's mounted on the vessel. And that deck unit is solar, so it doesn't need to be charged. The deck unit then transmits the data via cellular or satellite to the ZebraTech cloud server. Right now, most of our deck units are cellular. We're developing a Wi-Fi one because it turns out many of the larger fishing vessels actually have Wi-Fi on board. And then we're looking into developing a satellite deck unit as time goes on. And the key here is some vessels are within cellular range most of the time they're fishing. Others can spend up to a week outside of cellular range. And once we're at a week, we're not within that 72 hours that is our near real-time data cutoff for assimilation into our ocean models. So we are rolling out our Wi-Fi deck unit next week. We're going to begin trials on that. And for now, we're actually getting great results with the cellular deck unit in most locations. So once the observations get to the ZebraTech cloud server, they're pushed to us at MetOcean, where the data is automatically quality controlled, saved in CF compliant format, and then ingested into a database where the ocean modeling team can access the data. We also are creating some observation products that are independent from the models of subsurface temperature. The other thing that's worth mentioning here is the fishing observations themselves are the intellectual property of the vessel owners. So we provide the observations directly to them. And then we provide the improved ocean models, the graded ocean models via public access. So anyone can access them. For many organizations, it's free unless you start using it for commercial gain. But the actual raw fishing observations generally are not available to the public unless we get specific permission from the fishers. The big sensor requirement is that the whole process is automatic. So once the fishers have to be involved in manually offloading the data, it becomes much less of a reliable process because they have other priorities when they're at sea. So our system requires no human intervention on a daily basis. Only after 2 years, the battery needs to be changed and the sensor needs to be calibrated. But other than that, once the hardware is installed, no one needs to touch it. It also needs to be mounted on and be able to withstand impact from a range of fishing gear. It's often a pretty intense environment. It's low cost and lightweight, so it's easy. It doesn't impact their fishing operations. The position of the observations is logged by the deck unit. So we're actually getting vessel position, which sometimes can be slightly different from the fishing gear position. So that involves some post-processing. We have 2 sensors. One is rated to 200 meters depth and the other to 1,000 meters depth with a depth accuracy of about 2 meters. The temperature accuracy requirement is 0.1 degrees Celsius, but we're actually getting closer to 0.02 degrees Celsius, and we're working to have the sensors certified to that. We also have variable sampling of the sensor. So when the sensor is profiling, which means the pressure is changing rapidly. So as the fishing gear is dropping, we sample more often, and that's every 1 second. But say you have a sensor on a lobster cray pot and it's just sitting on the bottom of the ocean, we sample every 5 minutes. So we've met all of these requirements. Our trials have completed that section of the process. And now we are working on the Wi-Fi deck unit. We have a new wave algorithm, which basically changes how the sensor samples when it's in big swell conditions. And we are almost finished with the database ingestion process. So here you can see we have 4 Moanas, the blue sensors mounted on a cray pot. They're just zip tied on with some reference sensors. And here is a sensor in its protective tough jacket on a trawling gear vessel. And this is what the sensor looks like. As I said, here they are mounted on a pot. And it's about this big. They're very small and very light. So we also have developed, we found we needed to have a tough jacket for some conditions so the sensor doesn't get crushed. And below here in the bottom left, we have a range of mounting hardware that makes it easier for the fishers to mount this on gear. This is a net plate, so the tough jacket attaches to it and then it can be lashed to a fishing net. We've also done some comparisons with a high precision reference sensor. So this is an early on test with temperature on the y-axis and then time on the x-axis where it was deployed for about 10 days. The green line is the temperature according to the reference sensor, and the red and orange dots are the Moana sensors, and you can see they match up very closely. One of the new aspects of this program is developing quality control for fishing data. And as I said, we're doing this in conjunction with the Bering Data Collective. And the way that works here is once the data gets pushed from the ZebraTech cloud server to the MetOcean server, we automatically quality control all the data that comes in. Then that goes to the MetOcean observations database where we only ingest good data, and the modeling team can use it straight from there. we also automatically email plots of the data back to the fishers. And we decided on this based on conversations with them of what was most useful to them. And this data delivery aspect of Tiro Moana is constantly evolving. So as we get feedback both from the modeling team and from the fishers, we improve our procedures. Another aspect of the observations database is we're pulling the data into a sensor monitoring system. So we find that we have about 20 trials that have happened so far, being 20 different deployments of the sensor on vessels. That sometimes a sensor gets left on a net and doesn't go back in the ocean, or it doesn't get installed, or the battery voltage drops, or things like that. So to keep track of all of that, we have a sensor monitoring, we're developing a sensor monitoring system that will allow us to call up a fisher and say, hey, your battery is low, we need to change it. Or, what happened to the sensor? We don't see that it's transmitting data anymore. So we're working on that now. Right now, much of it is manual, but we're working toward it. And then we also, as part of our QC, need to process the position based on the fishing gear type. So as I said earlier, the deck unit is measuring the vessel position. So if somebody drops a lobster pot and then drives away, we need to know that the position of the sensor actually isn't changing. So we've developed some quality control codes to do that based on whether the fishing gear is stationary or mobile. We're also applying standard oceanographic temperature and pressure observations quality control based on international standards. In addition to some fishing specific quality controls, such as things like vessel speed, to make sure it's not actually on an airplane or something like that, which does happen. So the QC data goes into our observations database, the OBS API, and then we provide the data back to everyone once it's quality controlled. This is an ongoing project, and we're constantly improving the quality control of fishing data. Currently, we have sensors on 12 vessels all over New Zealand. So this map in the bottom right-hand corner shows where we've deployed vessels and where they've been fishing in a very general way. So you can see that we've covered a good chunk of New Zealand. Anywhere there's a blue box, we've had vessel deployments. And we're working on deploying vessels in these missing regions, in addition to additional vessels where we already have observations. So as of January 24th, we had 898 deployments of the sensor, and most of those have occurred since the beginning of October. So we've been able to test our data pathway, including quality control, on, at this point, this week, over 1,000 profiles. So up until now, our deployments have mostly been decided by physical ocean conditions, such as swell and currents. But we're starting to roll out our sensors to a broader range of vessels. So we're trying to cover all the types of commercial fishing gear that it makes sense to deploy these sensors on. And then also making sure we get observations in the regions of the Moana project case study. So that's in the Bay of Plenty up here and Kaikoura down here. And so as we move forward with this, we are trying to roll out to as many commercial vessels as possible of those 650. Our baseline is 125 vessels, and that's over the next year. So we're looking at rolling out to 10 vessels per month in the next year, approximately. We've had really good engagement from the fishing community. So as I said, the Fisheries Inshore New Zealand, the Deepwater Group have connected with us with many different fishers. NZ Rock Lobster the same. We had great publicity from the Seafood NZ magazine, and the big fishing companies and independent fishers in New Zealand really want to be a part of this, and have been massively helpful in helping us trial the sensors, improve them, and spread the word to get it on more fishing vessels. This plot in the bottom left is a sample plot that we send to the fishers, although we include a map generally, but we can't share their position. So I've removed it for this presentation. But we have depth, on the y-axis over time on the x-axis. And you can see this fishing gear is deployed. It drops down to about 50 meters, goes along the bottom of the ocean, and then is retrieved to the vessel. And temperature is shown in color. So this dark blue is the temperature at about 50 meters. It's colder, and then we get warmer around 0 to 20 meters. And this is courtesy of the skipper, Alan Basilage, and his vessel, the Kathleen G, that he was nice enough to let us share this for the presentation purposes. So there's a lot of benefits to the seafood sector. I covered it already a little bit. Basically, it allows them to more efficiently target the species they're supposed to catch and avoid the ones they aren't supposed to catch, particularly endangered species. And that leads us to a more sustainable blue economy and a more sustainable seafood sector. So fishing organizations have already started using both their observations and our model data in trying to improve their operations. There's also nationwide impacts for all of Tiro Moana, and that it's tied to the other themes of the Moana project. Everything we do here is so closely tied to the other themes. It would be great if we had time to present all of it, but we do not. So it improves our ocean predictions, operational timescales. It helps us understand ocean dynamics around New Zealand, including marine heat waves. So we just deployed last week at MetOcean a marine heat wave forecast tool that is based on the backbone model that came from the Moana project. These observations are also used for model validation verification, and we're providing public access to the ocean model and to our future subsurface temperature products. And then encouraging users to share their observation, or data holders to share their observations on the NZODN. And then lastly, it's engaging the community, in the case of Tiro Moana, specifically the fishing community, in the scientific and ocean observing process. It's a huge project. We have many partners from around New Zealand and internationally shown here, and I would like to thank all of them for their contributions to this work. And thank you all for being here and joining for this presentation. Does anyone have any questions? Yeah. And thank you, NH, for having me.
Okay, so we have 3 questions that came up during your talk. So the first one is from Jack Dibb. If you want to chime in, that feels free to do so. So he wrote, have you mounted some of the Mangapore sensors on CTDs to establish quality? Sounds like a lot of testing is focused on reliability. Maybe just answer this with the co-deployment of reference sensors.
So we haven't mounted them on CTDs, but we've mounted them with other high precision reference sensors. I think the reason we haven't done CTDs is primarily because CTDs are also measuring salinity, and they are quite expensive, partly for that reason. And we don't actually have a salinity sensor on this temperature sensor. So we've been mounting it with similarly high precision reference sensors. And that's been ongoing. So we actually have 2 out right now. And they've matched very well, both pressure and temperature.
Okay, 3 more questions from John Kelly. First one is, what other data sets besides the water temp profiles from the fishing vessels are simulated into the ocean forecast modeling systems? Okay, so
there are probably people who could answer that better than me right now, maybe even John. But so right now, the ones I know of are anything from the Cora in situ database. So that's Argo and drifters, and then anything else they have there. You're probably familiar with that. If not, it's the Copernicus CMEMS Cora database. You can Google it, and online they explain what instruments are included there. So we're anything from there, and then also sea level anomaly altimetry from satellites.
Okay. Do you plan to make the sensors available to recreational fishing vessels as well?
So we've looked at that. It's a bit, if anyone has any suggestions on this and would like to collaborate on it, I am more than happy to listen and to work with you. The problem with that has been how exactly to do it, because most recreational fishers are deploying a fishing line, and the sensor is a bit large for that. But we're working with some partners in New Zealand on developing a sensor specifically for recreational fishing vessels. That will be a slightly separate project that's closely tied to the Moana project. But we're actually working on a proposal for that right now.
Okay. What is the core 3D oceanographic forecast model used by the forecast modeling system?
So I think if I understand the question correctly, it's ROMs, hopefully is what they're asking. Again, I can, if you want more detail on the ocean modeling system, I can put you in contact with the modeling team lead, João de Souza, who can answer all of those questions much more thoroughly than I can. But the backbone model for New Zealand is ROMs, and we have some nested CCOM models also.
Okay. John, okay. John says thank you. Jonathan Rees says, fabulous talk. Have you used models to identify areas and depths to fill data holes? For example, in strong gradients, fronts, mesoscale, eddies by sensor type from a wet and cold UK. Oh, that's where he's from.
Okay. So informally, yes, our ocean modeling team requests that we deploy sensors in certain locations, particularly where there's strong fronts and things like that. And we have been able to target those. We're going, Colette Carey at UNSW is going to be doing an analysis in more detail from a modeling perspective of where we should be deploying sensors. And once that's done, we'll target those areas in particular. But for now, we're looking at areas of interesting ocean dynamics where our modeling team requests that we put sensors. And so far, we've pretty much been able to do that. It's a little bit challenging sometimes because we can only observe where fishing vessels go. So we can't say tomorrow at 2 p.m. we want an observation here unless we have a very nice fisher who's willing to do that. But yeah, we have been able to begin doing that, and that process will be ongoing as we deploy more sensors and we understand more the impact of the observations on the models.
Okay, I have one more question here. Curious from Jack Dibb. Curious why there were so few CTD profiles all around the North Island and south of Fjordland, LE plots showing historic data, not interesting regions or somehow proprietary?
Right. So those CTD profiles came from trawl surveys. So it's where the trawl vessels are fishing. It's also not a complete data. So those aren't all the CTD profiles from around New Zealand. There are other data sets that NIWA hold and other organizations too. That was a sample data set I chose that's from trawl surveys. And so I'm guessing that is where most of the trawling happens around New Zealand. But I'm not 100% sure about that.
Okay.
Thank you. It looked like people were being forced to stay away from the coast for some reason, especially all around the north end of the North Island.
I will have a discussion with that about them. I'm curious too, now that you say that, exactly how they choose. This is done with the Ministry of Primary Industries and the seafood sector. I'm not 100% sure why they chose those locations, but I'll find out. Yeah.
Thank you.
Yeah.
Does anyone have any other questions? You can just unmute yourself. Okay, so I think we're done. Thank you so much, Julie, for this talk. It was very interesting. And thank you everyone for joining us. Enjoy the weekend and see you next week.
All right. Thank you very much, Coral, for the invitation and for everyone who organized this. Yeah, it was a great opportunity. So thank you. And thank you again for everyone who joined. If anyone has any additional questions, please send me an email and I will be happy to talk about it further. Or if anyone has any interest in collaboration, please let me know. So thank you.
Great. Thank you so much, Julie.